d by dx or d by dt of t to the power n will be nothing but n t to the power n minus 1. And on the other hand, if I've got integral t power n dt, then this can be written as t to the power n plus 1 by n plus 1. So these are the only two formulas that we will be using for the calculus that is there. And as and when needed, we will look at other formulas that are there. Now, we know that there are three equations of motion. The first one being v is equal to u plus at. The second one, s is equal to ut plus half at square. And the third one, v square is equal to u square plus 2as. Now, all of these three we have derived graphically. So now let us go ahead and derive all these equations using integration and differentiation. That is the method of calculus that is there. So the first equation of motion is v is equal to u plus at. Now in order to arrive at this, we will take acceleration, which we have seen it as nothing but dv by dt. That is the rate of change of velocity. We will go ahead and do a small change. So dv is equal to a times dt. So similar to algebra, we cannot do it, but here algebraically what we are doing is we are making sure acceleration is time dependent. And now we will apply the formula of integration that is there. That is integral dv is equal to a dt. So I have another integral. So both the sides I have put my integration sign. Now before we proceed, a couple of things that we have to see. Here velocity and time we will have to define, because dv and dt are the values that are going to change. So we will have to define their limits. So when I tell define their limits, what is the meaning of that? That is, it's as simple as telling that when we are looking at the starting and the finishing point, what it is. So for instance, let us look at the time when it is 0. My velocity, I can simply write this as v is equal to the initial velocity. And when it is at a certain time t, the velocity is the final velocity. So we will have to apply our limits that are there. So dv varies with the limits from initial velocity to final velocity. At the same time, time varies from 0 to t. So this is how we usually write it. So t is equal to 0 to t is equal to t. Now let us go ahead and solve. If we see the first, let's say the LHS. Integral dv is nothing but integral v to the power 0 dv. So the limits are from u to v. Now according to the formula that is there, t power n dt was t to the power n plus 1 by n plus 1. So here I can write it as v to the power 0 plus 1 by 0 plus 1. And this is how we are going to write the limits. So as soon as integration is performed, we are going to make sure that we put square brackets and we write the limits. As in any case, it has to be upper limit, that is the final velocity minus initial velocity, that is upper limit minus lower limit. So I have v varying from the initial to final. So we get this as v minus u. So this is our LHS. Let us look at our RHS. In the RHS, we have got integral a dt, where time is varying from 0 to some value t. And here if we see, acceleration is in a way independent of time. Though the formula is dv by dt, here when we see a is not a function of t. So we can write it like this. So a is a constant, we take it outside the integral. Integral t is equal to 0 to t is equal to t dt. So what I will do, again, just for simplicity's sake and for understanding, I'll put it as t power 0 dt. So this becomes a t to the power 0 plus 1 by 0 plus 1, t varies from 0 to t, which is equal to a times t, which varies from 0 to t, which is a t minus 0 is equal to a t. This is our RHS. So let us equate. LHS is equal to RHS. I will write my value, that is that the integral will start from there. Integral dv u to v is equal to a integral dt 0 to t. And the LHS we found it to be v minus u is equal to at, or v is equal to u plus at. So this is the first equation of motion that we have derived using the method of calculus.